Welcome, everyone. We are beginning the event now. We're going to give 5 minutes at the start now, just as people join up, and then we will begin in earnest. Right. Welcome, everyone. We are going to begin now. So thank you for joining us here today for our SAIEE Lightning chapter, our first webinar of the year. And as you will be aware, this webinar is titled Current Developments in Lightning Data, Standards, Statuses, and Uses. And I think we're in for a very interesting talk here today. Lightning data is becoming so prevalent in our industry nowadays, and we have numerous sources and providers of data, and often it's unclear exactly what data we're working with and how it fits into the new standards with the new IEC 62305 edition out. There's already changes to that standards that Lightning data plays a large role in how to estimate some of the parameters, our flash density and our ground strike point density parameters. The IEC 62858 standard, talking around the performance of lightning detection networks and such. These are all quite new developments and very relevant to a wide range of our engineering and electrical industries. And so I think today's webinar will be very exciting and interesting on this subject. So just so you know who I am, my name is Dr. Hugh Hunt. I'm a senior lecturer at the University of Witwatersrand here in Johannesburg, and I'm also the chairman of the SAIEE Lightning chapter, so I will be your host tonight. But I really shouldn't talk too much. We've got far more interesting speakers who will talk to you with more interesting information than I can provide you. And with that said, I would like to introduce our first speaker. This is Mr. Stefan Pereboy from the company METEORAGE, the vice president of METEORAGE in France. And Stefan has recently been involved in our South African industry and lightning detection industry more as part of the partnership with the South African Weather Service. And METEORAGE and the Weather Service are working together very well, bringing us highly accurate and modern, up-to-date lightning detection network data. And Stefan is going to take us through some of the context around that today, and in light of different standards and how lightning data is relevant to the field. So with that said, Stefan, please, I'll hand over to you. Thank you.
Thank you very much, Hugh, for this introduction. And so before starting, I will try to introduce a bit the subject. Lightning data is used in lots of applications, in many fields, just like you introduced the subject, Hugh. And so severe weather monitoring, nowcasting, aviation safety, and power grid management, military and defense, and so on research. I forget for sure some topics, but and on the other hand, thanks to the technological progress made in electronics and signal processing recently, so lots of lightning locating systems have been developed and deployed worldwide. So, however, the different technologies used in such systems, the different operating mode used by different operators, different countries, and this may affect the quality of the lightning data. Okay, and so consequently, the resulting services based on this data might not meet customers' expectations. And this is the objective of my presentation, is to focus on this point, is how can IEC international standards can help operators of lightning locating system to provide accurate and reliable data. Second, engineers to build efficient lightning protection systems and for their assets. And finally, end users and customers to better understand and be confident in lightning data. This is the purpose of my presentation. And this is the general overview, starting with a very fast introduction to lightning and maybe to lightning locating systems for some of you, a presentation of the lightning datasets collected by such systems, and then finally, the main point of this presentation would be to review the main topics, the main recommendations in this standard IEC 62858 dealing with the lightning locating systems and lightning data. And finally, I will conclude. So, as an introduction, I think it's important to introduce lightning. That is a very complex electrical atmospheric phenomenon. It's a surprise for nobody, I think, attending this this webinar. But the basics is that these electrical discharges generate electromagnetic signals that can propagate over large distances and in a very large spectrum, ranging from very low frequency up to very high frequency, including up to gamma rays in some circumstances. I have I can show you. I don't know if you see my mouse here, but on this schematics, this summarize the way how a lightning locating system can pick up these signals and locate and process and locate the corresponding discharges. So as you can see here, you have cumulative numbers generating electrical discharges, and these discharges are going to generate electromagnetic signals that are going to propagate within three modes, different modes: direct propagation, ground wave propagation, and ionospheric reflection propagation. I won't go too much in details because it's too much technical and it's not the purpose of the presentation. But the thing is to introduce the fact that in order to locate electromagnetic discharges, signals, you can use some techniques, different techniques. So that is based on the electromagnetic signatures analysis. So I'm talking here about ground-based lining locating system using remote sensing technique, meaning that there is no direct measurements of the currents flowing in these discharges, and using trilateration techniques, meaning, in other words, that we are using difference of time of arrival or direction finding or combining both methods in some cases. Okay, so and beside these ground-based lining locating systems, now more and more tend to appear optical instruments on board satellites, like the GLM in covering the Americas, let's say, and more recently the MTGLI covering Europe and Africa. So you have some pictures showing you some sensors. All the sensors, electromagnetic sensors like this one from Vaisala, this one from the LMA station, which is very famous in the research field, are based on antennas picking up these electromagnetic signals. For the satellite, it's a bit different as the optical signal is picked up. Okay, so if something, if you must remember something, that lining locating system, the acronym is LLS, operating in low frequency, can cover large domains with reasonable operating cost, the reason why they are mainly deployed worldwide. And so this result, as a result, they are the most deployed worldwide. Okay, they provide the most of the lining data in many applications are based on low frequency lining locating systems, and they are operated by commercial companies like METEORAGE and some others in Europe and worldwide as well. So having said that, so the landing data set collected by such systems are a kind of these systems are able to localize and to detect cloud-to-ground return strokes, meaning discharges occurring between the cloud and the ground, and also I'm sorry, but I don't know who is playing with that. I cannot see my presentation. So yeah, and cloud to ground, I was saying, and as well as intra-cloud discharges. And these are the raw data, meaning that these systems collect these individual discharges. And based on these individual discharges, individual data set of discharges, it's necessary to apply some algorithms in order first to group all these discharges in a consistent entity, which is called the flash, aiming at reproduce what the phenomenon that a human eye can see when a lining occurs somewhere, or a second algorithm, which is called ground strike points, which is which aims at detecting the different points in lining, because in some cases, cloud-to-ground flashes might hit the ground not in a single point, but in several points. And these points are labeled ground strike points. And of course, in terms of risk assessment, these points represent the danger, as there is an attachment point to the ground or to a structure or to whatever, to some assets. And so this data set is actually I show you here on this diagram the hierarchy of the data, and you see that starting from the bottom line, you see that you have the strokes, meaning that this is what I was explaining. The LLS detects very raw data, which are the individual discharges, and then you have this flash grouping algorithm collecting all the strokes occurring in a flash within one single entity, which is the flash. And inside this, in between, you see there is another level, which is the ground strike points. In order to illustrate this rather complicated data sets, I have taken a real example from METEORAGE. This flash occurred somewhere in France some weeks ago, and so you see. So this is a flash. If you look at the picture here, this is exactly what what we call a branch or forked cloud to ground flash. You see, meaning that you have two different channels separated by a distance, hitting the ground in different distinct points. And if you apply this photography to the data presented here, you see that you have the green signs. So this square here and this minus here and another one here are the raw data collected by METEORAGE. And you see that these are the return strokes located by METEORAGE. And easily you can see that there is a separation distance in two different groups, and these groups are identified as the ground strike points. And here the method used by METEORAGE to identify the ground strike points, in this case it's rather easy, as it's only one return stroke occurring here. So the ground strike point is the same location as the return stroke. In this case, we had to make a kind of average in all the position of the return strokes. All the return strokes are not located to the same position. They should have, but because of some errors introduced by the system, you have some location errors here, explaining the distance you have in the several subsequent discharges occurring in the same channel. Okay, but what is important here to understand is that here you have the return strokes in green. In yellow, the star are the ground strike points, and here the square represents the flash. And the flash is the result of the grouping of the return strokes. And you will see later how it is important to understand the difference between a flash, a lightning flash delivered by a lightning locating system, and the ground strike points. You see here there is a single point of danger if you consider the flash. If you consider the ground strike point, you will get two different danger point where a danger may occur. I will get back on this notion later on. So the review of the IEC 62858. So the main motivation of this standard is trying to standardize. It's for standard, you would say it's quite normal, but to standardize all these measurements, because landing data is not the result of direct measurements. It's remote sensing, meaning that you have limited detection efficiency. You might not detect all the discharges. You have, as I presented previously, some location errors that are, yes, different range of location errors. And you also have some misclassification between discharges occurring inside the cloud or between the cloud and the ground. And so these errors just qualify the data set you are using. And of course, the technology and the different technology and the operation of the system highly influence, I would say, the data quality. So this was the first reason for this standard. And the second reason was lightning density is computed from lightning data collected by lightning locating systems. But it exists several ways to compute the lightning density. Should you consider only the return strokes? Should you consider the flashes? Should you consider the ground strike points, etc., etc.? And so the second objective of this standard was to standardize, really to define, to determine, to recommend a method in order to compute lightning density. So this standard addresses the two issues presented in order to guarantee reliable and relevant lightning data density value, providing some recommendations. And there are three kinds of recommendations in this standard. The first one is the minimum performance the landing locating system must achieve in order to deliver data with enough quality for applications. The second is the flash grouping, how to group the different return strokes within a flash, and how to identify the ground strike point inside a flash. So these are there are also some recommendations in the standard for this algorithm. And finally, the calculation, the method to compute the landing density parameter. So the first, I will go through the requirements for on the landing locating system performances. So roughly, so of course, the performance of a landing locating system depends very much on several factors, some more important than others. But you know, the distances between sensors, the sensor sensitivity, the telecoms, collecting the data and transmitting the data to the central computer, etc., etc. Of course, all these parameters, these operational parameters may influence the quality. So we are used as landing locating system operators to define the performance of our systems based on three different, not only three, but three main parameters that are first, the cloud to ground detection efficiency. Here we are focusing on the flash cloud detection efficiency, which is computed as the number of flashes detected by the system in respect to the real number occurring in nature, which is a bit of a challenge sometimes to know this parameter. The location accuracy, computed as a distance between the location provided by the system and the real location of the stroke. And finally, the classification accuracy, which is computed as the number of detected stroke and classified as CG, crowd to ground, in respect to the total number of return strokes occurring. So these three parameters, they are, just I said, they are sometimes very hard to estimate. The techniques to estimate such parameters might be really costly in time, in money as well. And this is something which is highly technical to achieve. But nevertheless, some of these techniques are discussed in the document, in the standard, and we are talking about network self-referencing, so meaning that we are using some parameters from the landing data set to assess the quality of a landing data set. Just as an example, we can rely on the number of sensors detecting a return stroke in order to see if the system behaves well. We can also compare a test data set in respect to a reference data set. And of course, the best would be to compare against what we call ground truth data based on video records, instrument towers, recording the current waveforms, etc., etc. But finally, the IEC recommendations are, in order to deliver usable landing data, flash detection efficiency, cloud to ground flash detection efficiency must be above or higher than 80%. Location accuracy for the strokes, return strokes, must be below 500 meters. And the classification accuracy between IC and CG must be superior to 85%. And of course, all these three recommendations go along each other. I mean that you must achieve these three values of parameters in order to be able to deliver reliable data for applications and for landing density calculation. So the second point is the flash grouping and ground strike point algorithm. So again, LLS can detect CG and IC pulses. These discharges are grouped in flash, aiming at representing the landing as observed by human by a human observer. And so this algorithm is based on 3 different parameters. So in respect to the first discharge, the first return stroke located by the system, so the subsequent strokes must occur within a delay not higher than 1 second, okay, which is, we all know this now, it's a pure limitations. I think that 95 or 98% of all the flashes have a delay less than this 1 second. We know that some have much higher delays, much higher durations, and I think that the record by the GLM is something about more than 80 seconds or so. But nevertheless, this is something that is quite in use among the landing locking system operators. So we use this value of 1 second. That must not be, the separation between the first return stroke and the last return stroke of a flash mustn't be above 1 second. And again, another parameter, which is a distance parameter. The distance mustn't be higher than 10 kilometers in order to that return strokes is grouped with a previous return stroke in the flash. And finally, there is also a parameter stating that the delay between 2 subsequent strokes, meaning between the first and second and third, etc., mustn't be above half a second, 500 milliseconds. And based on this, using this, of course, it's possible to compare the flashes collected by different technology, different landing locking system based on different technology operated by different way. So because this method is unique, it's possible to compare landing data. And I just remind you that by convention, what I was presenting in the previous slide, the flash is characterized by the first return stroke for the CGD flashes and the first IC pulse for the IC flashes. So this is pure convention here. There is nothing based on scientific research, etc. So this is just by convention, a flash. You must know a flash is characterized by the first return stroke, meaning location and peak current, polarity, etc. Okay. What is important here is that the CG flash data is used to compute the ground flash density, what we call the NG, number of ground flash. Okay. The ground strike points, I do not present here the ground strike point algorithm because I think that the speaker following me is going to give you some details on this algorithm and landing data set. But the ground strike points are used to compute the ground flash density, just like the previous sentence. You see, it's still ground flash density, but based on the ground strike points. And it's called the NSG. And the IEC 62858 recommends using the NSG because, as I introduced this data is much more representative of the real danger occurring on the ground, as it detects the real points of danger compared to the flash that is just picking up the first ground strike point. That's it. So the standard recommend using the NSG when, of course, the data is available. It's not always possible. Not all the operators are able to provide this. So this is the case for SOS. They can provide such data set, and this is the important thing to think about. And finally, so the computation of landing density, it's quite obvious. So the objective, of course, of this recommendation is to guarantee a reliable value for landing density, to provide a uniform method, making different landing dataset comparable. And so this is based on 2 main recommendations: a minimum period of data on which you can compute your landing density. So it is recommended using 10 years. So why 10 years? Because more than 10 years, you may catch some effect of the climatological the change due to the global warming. This is something that is that is something. It was a choice we made for this 10 years. And what is important is not less than 10 years, because in order to avoid the natural variability of landing activity. So this is quite important. So not less than 10 years. And then finally, also the grid cell size, which is quite important. We stated by that the number of flashes or ground strike points, I mean events, inside the area of calculation must be greater than 80. And why 80? This is a figure that guarantee an uncertainty of less than 20% with a confidence level of 90%. And this is based on the rare events law, and it's used to be called by the Poisson law. Okay, so this is for rare events. So as soon as you get 80 events or more within the domain of calculation, you can be sure that the uncertainty is less than 20%, which is the aim, the main objective of this standard. So comments, because it's not so. So I put the formula for the calculation there. So this is quite simple to understand. This is the total number of events, whatever flashes or ground strike points, divided by the area of a cell and multiplied by the duration of the data set. Some comments. Of course, the size of the grid cell must be as small as possible, ideally 1 by 1 kilometer, meaning that the assets you want to consider for the risk assessment, and okay, this area must surround as closely as possible these assets. But the drawback here is that in some regions, like we have some in France, it is not possible to obtain 80 events, and reasonably we must increase either the size of the cell or increase a bit the duration of the data set. Otherwise, we cannot reach this value of 80 events. And in some cases, where the landing activity is very low, it's even not possible to obtain the 80 events. These are just some comments, and as users of landing density, you must be aware of all these things. And finally, it's time for me to conclude. So the development of LLS based on several technologies produce a variety of landing datasets that might not be always well documented and consistent, that are sometimes difficult to intercompare each others, and that are sometimes of poor quality. And the IEC 62858 attempts to draw attention for the end users and of these data sets, to draw attention to landing data user, giving information for recommendation about the minimum performance of LLS. Pay attention to these performances. It's really important if you want to rely on very good quality landing data. Of course, the performance of the landing locating system must achieve a certain level. Then the data processing algorithm used by ELS operators. Just ask the question to your operator how they compute the flash grouping and also the ground strike points when it exists. The landing data must also be used for landing risk assessment, flash or ground strike points, and the method to compute the reliable statistics have been presented in this presentation, and of course with more details in the standard itself. And of course, so I focused my talk here on the 62858 standard because it's dealing with a landing locating system, and lightning flash density calculation. But of course, this standard goes along with other standards presented previously by Hugh. I mean here the 62305-2 dealing with the risk assessment, and of course the IEC 62753 dealing with thunderstorm warning system. Some of these systems are based on lightning data as well. So this is the end of my presentation, and I will let the floor to Andrew, I guess. No, to Rydal, sorry. Sorry, Rydal.
Thank you, Stefan. Much appreciated. I think we will move on to the next presentation, but if anyone has questions, please put them in the chat there, and we'll get to them at the end of the overall presentation. So, and Stefan, you're welcome to answer any questions that someone posts there.
Yeah, sure.
So I'd like to introduce our next speaker, which is Mr. Rydal Jardine. And Rydal is the technical service manager at SAIEE and at the South African Weather Service. And Rydal has been working with the South African Lightning Detection Network and the actual installation of the sensors and much of the technical areas of the network, along with the data, for more than 20 years now, since its inception. So he really has a wide range of experience in this area. And Rydal is also currently pursuing his master's in electrical engineering at WITS, and he is the deputy chairperson of the Lightning chapter. So, Rydal, I'll hand over to you shortly, but I thought I'd also mention that you're being backed up by your colleague Morne Geben, who is the lead scientist at the Weather Service, and Morne is completed his master's from the University of Pretoria and is currently doing his PhD, and really works with the remote sensing, weather data in general. Done a lot of work with the Lightning Detection Network, and Morne is also responsible for some of the first lightning flash density maps we produced for South Africa since the network's inception. But Rydal, I'll hand over to you to present, and Morne is there to back us up with answers to things in the chat if needs be. Please go ahead.
Thank you very much, Hugh, and thank you for the introduction. As said, I'm Rydal Jardine, and I'm being supported by Morne Geben from the South African Weather Service, and I'll be introducing the current status of the South African Weather Service network. That being said, we're going to touch basically on the history of the Lightning network and research within the South African Weather Service, the growth over the years that we've had this network, the sources and capacity building exercises that we've put in place, the future and forward looking of the network, the purpose of why the South African Weather Service needs this network, and then of course also the network's compliance and performance at the current state, as well as lessons that we may have learned, and then of course in conclusion, what is the way we intend this to move as not just a South African but a Southern African network. That being stated, first thing that I need to state is that around 2005 we started the current network, which is the Vaisala Lightning Detection Network, with 19 sensors in 2005, and we've recently moved it up to 26 sensors now. The upgrades has taken us approximately 5 years, and the network, as I've indicated, is going to be known as the Southern African Lightning Detection Network, because it does not only consist of the South African Weather Service owned sensors, but also third-party owned sensors. And then the network has expanded and reached the baseline of cost recovery so that we can be able to plow back the funds that the South African government has invested in the network in performing the services to the country. That being stated, over the last years, as I've indicated, we use this network. It does both the time of arrival technology applications as well as magnetic direction finding technology. It was originally a state investment and is now moved towards a public-private sector environment where we actually have infrastructure sponsored by the industry as well as space or allocation for our infrastructure to be installed. There's also strategic technology and application partnerships that we've engaged on. And this covers also our collaboration with the country's universities, cross-border collaboration with our neighboring countries. We also ensure that our members are members of the South African Engineering Council, as well as the voluntary engineering bodies within the environment. We also work very close with the standards, compliance, and engineering bodies to facilitate that we comply, but also that you get good quality within South Africa from the Weather Service. In our client base, we currently have the South African electrical power generation or utilities as part of our main clients for their overhead networks, for performance of the systems and the designs, as well as for asset management of their lines and for fault correlation. In the aviation industry, it's also used to safeguard the aviation industry from danger that could occur when lighting gets too close to the airport, and therefore they use focus areas that is divided up in rings of about 5-kilometer radius up to about 15 kilometers away from the airport. For that protection, we also have the insurance industry that is using the lightning for claims and verification thereof. We have the mining industry that use it for safety of their operations, as well as the astronomy research industry that uses this information. Resource and capacity building with South African Weather Service. The South African Weather Service has currently invested more than 100 million rands already over the past 20 years just on the infrastructure alone, with an average of about 40 million per year or annually on the operations and maintenance of the network. We have ensured that there's a dedicated team around the country consisting of about 20 dedicated human resources, as well as to ensure that there is support for the detection and the tracking capability. We conducted annual capacity building and improvement processes, facilitate the upgrade of the network to the latest technology, ensuring that we are compliant to the international standards. Our forward looking for now is to say that we have actually expanded our network into the Southern African lightning environment, with some of the countries already participating, having the same sensors or using the same network that we are using, such as Eswatini. We have neighboring countries that also got their own other alternative networks, and we work closely with them as well. The support and improvement of the lightning research capability and awareness within the country, as well as contributing towards the saving of life strategies, both, as I've indicated, the South African Weather Service mandate, as well as the mandates of those entities that we work closely with. We are busy at this point in time also applying some automation and artificial intelligence maintenance and support and analysis principles to improve the operations of the network. The main purpose, as indicated, the South African Weather Service, its main mandate is the protection of life and property within South Africa. And it's for that reason that we therefore invest in these type of networks, providing a world-class research and technology background for research and also supporting the environments that might need to utilize this data. We ensure timely and accurate provision of life-saving meteorological awareness and incident investigation, provide and support the events of meteorological disasters and storm tracking. We're providing value on the return on investment for the country and its people. And then, of course, as we've said on the compliance issues, I know that the previous speaker already spoke a lot about this, but what is important for us to raise maybe on the slide is to indicate that it is in line with the South African Weather Service Act of 2001, and that is specifically Section 4, which refers to the severe weather warnings as well as the thunderstorm warning systems and the protection against lightning from thunderstorm warning systems. Then, of course, with the IEC 62858, Section 5, there is validation of our network that we needed to comply with, and these consist of the network self-referencing, the rocket-triggered lightning and tall object studies, as well as the video camera studies and the intercomparison amongst lightning detection networks or the lightning location systems. That being said, at this point in time, with studies that has been performed between ourselves and with the aid of the University of Witwatersrand or Wits University in Johannesburg, we have managed to achieve already with data from 2017-18 that we have a medium location accuracy of 68.5 meters. Once again, this is in line with the standard, as was explained earlier, and across the period of at least 11 years, which is the solar cycle that we needed to take in cognizance. That being said, here's just an example of that first study that we've spoken about, where it was done on data from 2017-18, and it was part of a presentation done also at the ICLP 2018 conference, and it spoke about 71 lightning events that took place with that measurement of the mean location accuracy of 68.5 meters. The second study that was also performed was a study that indicated that the cross-referencing between different networks to be able to tell us where the South African Weather Service network at this point in time was standing. And as you can see, there is quite good performance from the network. We have also then learned a number of lessons from this, and that is that within the African environment, which is a highly lightning intense environment, it is important that we have close collaboration, and especially in the side of the implementation, the maintenance of the lightning detection networks. And we need to improve electrical installations as well as the related earthing standards within the environment for longevity as well as sustainability of these networks. We work closely with the respective standard bodies, as we've indicated in South Africa, and engineering bodies, as well as some of our universities within South Africa. That being stated, the network structure and operation and maintenance strategy that we implemented at this point in time, as indicated, we've got strategically positioned personnel around the country that performs quarterly maintenance. We also have annual maintenance planning processes, which involves at least 4 preventative maintenance activities, plus additional 2 corrective maintenance intervals. And then we have strategic network support and optimization contracts in place. And these involve, like we've indicated before, relationships with METEORAGE, relationship with BioSala, and others to be able to support us to make sure we deliver the best possible service. And then from the industry, we have also got industry-aligned space holding alignment process, and we've got the capacitation and optimization internally in the South African Weather Service, and we're also looking closely at cross-border collaboration and capacity sharing with our neighboring countries. In conclusion, the South African Weather Service, as part of its role within the World Meteorological Organization, or WMO RA1 environment. We are the information hub for the Southern African region, and it is important, therefore, that we strive to assist with the improvement of the regional data collection. We expand the regional infrastructure coverage, and then also ensure that we improve regional collaboration and support. And with that, I thank you for your time. Thank you. Back to you, Hugh.
It seems you lost connection, so I will, while he's reconnecting, I will introduce Andrew so that you can continue the presentation. So Andrew is a postgraduate student at WITS and is working with you on a master degree in electrical engineering, and so he will present some of his research related to lightning. Andrew, up to you.
Thank you. Right, good evening, everyone. Tonight, I'm going to be presenting some preliminary work from my master's research. So the work I've done so far is the correlation between lightning flash density and elevation over eastern South Africa, Lesotho, and Eswatini. So for context, GSP characteristics are a topic of interest. You saw in Stefan's presentation. One of my colleagues has done a fair amount of research on it. And what I'm looking at now is how does topography, in particular elevation, affect lightning characteristics. So an interesting study was published last year by Dieter Pullman and his colleagues, and they mapped ground strike points across Europe, and they found that GSP's densities were low in the Alps and high over the Mediterranean and Adriatic seas. So no one has really looked at it in South Africa from that point of view. So my research would be map ground strike point density, and then I want to correlate that to elevation. So I don't just want a qualitative analysis, I want a quantitative value at the end of my research. And then I'm also looking at flash density and elevation. So I know some work has been done on it before, but again, I want to get a quantitative value for the correlation between flash density and elevation, and then I want to compare the two sets of results. So tonight, I'm just going to show you the work done on flash density. So I've chosen a region of South Africa. It's from 25 degrees south to 30 degrees south and 27 degrees east to 33 degrees east. And it covers the a fair amount of South Africa, plus most of Lesotho, the entirety of Eswatini, and a little bit of Mozambique. So why this region? Well, firstly, it's a high rainfall region. I mean, you can't have lightning without rainfall. So, if you took the Western Cape, for example, they have high rainfall, but the flash density is low. So it doesn't help using that area. So I've taken a high flash density area, and then I've taken an area with high topographical variation. So it includes the lowest point, sea level, and the highest point in the region, in the Drakensberg and Maluti Mountains. And another reason for doing a smaller region instead of the whole country is that South Africa has a variety of climates. And to get a good set of results, I decided to keep it in a region that is fairly consistent. So to give you a description of the region, you'll have to bear with me. I don't have a pointer, but we have the Indian Ocean on our east coast, so that's the dark blue section in the bottom right, where we have the southward flowing Agulhas Current. So west of that, in the blue section, we have a generally lower lying area that slopes slightly towards the west. And then above, to the west of that, you'll see a large green area that appears to be fairly consistent in elevation. It doesn't change much. That's our central plateau, and it's quite high. It sits at 1,000 meters to 2,000 meters. And then that reddish orange section would be a mountain range, the Drakensberg and Maluti Mountains. And they're very high. As you can see in this picture here, these peaks reach up to about 3,000 meters in some cases. And then if you look at the contrast between areas, it will look like a fine line. So say between the green and the blue, that's a mountainous escarpment. So it's quite a sharp change in elevation. It's almost like a wall that runs from north to south along the eastern portion of South Africa. So I won't go into too much detail here. Stefan and Rydal spoke quite a bit about lightning detection networks. But I just want to say, yes, my stroke data was obtained from the South African Weather Service. And what I've done is I've grouped strokes into flashes according to the standards. Stefan spoke about that in quite a bit of detail. And I just like to add as well that my data set spans quite a few years. It goes from the beginning of 2007 to the end of 2019. So it's fairly substantial and, in my opinion, quite reliable. So what is the methodology I've employed? So first of all, to obtain flash density, I've tessellated a map of South Africa into a grid of 30 arc seconds by 30 arc seconds in size. And this closely approximates 1 kilometer, which would fit the standard, the IC standard, where flash density is measured in kilometers squared per year. The reason I didn't take kilometers is because as you move away from the equator, the surface area changes. You'll have inconsistencies in your area of your grid cells, whereas with this, it's a bit more accurate. And then additionally, digital elevation data comes in arc seconds, and the data set I used was 30 arc seconds. So then the grid I've created here correlates nicely with a 30 arc second digital elevation model. So in these pictures, the top picture, I've just populated a region around Johannesburg with flash data as points. And then the bottom picture, I've zoomed in and you can see flashes binned into the little grid cells. And that's your flash density. You count the number of points within each cell and you get your flash density for that. And then I divided by the number of years in the data set so that we have flash density approximately per kilometer per year. So for calculating the correlation between flash density and elevation, I used the Pearson correlation. Many of you will probably recognize it. It's quite a common equation in statistics. And in terms of interpreting the results, if we get a correlation of 0, it means there's no correlation. -1 would say the correlation is negative, and a correlation tending to 1 would suggest that there's a positive correlation. So on the left, I've mapped flash density. On the right, we have the map of elevation. Sorry, the values are a bit small to see, but so essentially what we have is, I'll have to explain atmospheric phenomena first before I proceed, but basically a very generalized description of what happens is we have warm, moist air coming from the Agulhas Current in the Indian Ocean, blows to the west. This moist air gets lifted by the escarpment, or it comes into the escarpment and it gets forced up quite suddenly into the atmosphere, and we then have convective storms. And it makes sense. If you look at the flash density map on the left, the highest density of flashes is just to the right of the escarpment in it's like almost like captured in cauldrons along the escarpment, and then a fair amount on the plateau also has a high flash density. At the coast or in the low-lying areas, it's generally quite low. But something that's also quite interesting you'll notice is that you can almost trace the shape of Lesotho in the flash density map. So if you look at the elevation map, you've got that red area. And then on the left, you can see it in the flash density map. And that flash density is very low, which would seem to imply that flash density is lower at high altitudes. So here's the correlation map. We get a correlation of 0.44, which isn't bad. I mean, it's not a strong correlation, but it's a moderate correlation. So there's certainly something. And what you'll notice is along the coast and in the low-lying areas, the correlation is densest, and it's reasonably high. But the correlation I found was strongest along the escarpment edges and around the Drakensberg and Maluti Mountains. It's a bit tough to see here, but you can faintly trace the shape of the escarpment by looking at this correlation map. So I've plotted a linear regression here just to demonstrate my findings. And then something that's interesting is the flash density increases generally with altitude up to about 1,300, 1,400 meters, and then drops off suddenly. So it does validate, that dark patch sitting over Lesotho. Now going back to the correlation, with this correlation being strongest along these edges, it prompted me to think, well, okay, maybe change in elevation is something I should be looking at rather than elevation itself. So what I did was I resampled a 7.5 second digital elevation model to a 30-second digital elevation model, and I got change in elevation. So that's the image or the map you see on the left. And the results were very low, actually. The Pearson correlation was 0.128, which means the correlation between flash density and change in elevation is very weak. And you can see that in the correlation map on the right. But there are still certain areas where that correlation is still prominent. And it's like I said, it's tough to see here. I don't have a pointer. But if you look around certain like high-lying areas, you can see a strong correlation still. I should say areas of stark change in elevation. So I looked carefully. I was scouring the map in fair detail, and I picked up on a trend which I find quite interesting. And that is despite the fact that flash density may be low at high altitudes, when you have a ridge or salient or topography in that shape, descending from a high area quite far into a low area, you get high flash density and high correlation. So if you look at the top left image, that's our elevation map that we saw earlier. I've taken a snippet of the top or the northern tip of Lesotho. So the top of that red bit, you get a bit of the plateau, a bit of the coastal plain below. You can see that there, and you'll notice there's the ridges are like tendrils, like almost roots of a tree, extending from the red area into the yellow, and then from the yellow part into the turquoise part. Then on the right, I've mapped the flash density, and you can see it's still generally low at high altitudes, but on these branches that are spreading out, these ridges coming down, you can see the flash density is prominent, and you can almost trace the topography along these lines. And then, of course, in that low-lying area, we have a high flash density, like we saw earlier, at the bottom of the escarpment. That's still the same. Then at the bottom left, we have the correlation between elevation and flash density. And it's, again, you can see strong correlation along these ridges, so that it looks, you can trace the elevation map onto the correlation map. And then at the bottom right, it's the change in elevation versus flash density. And again, it's a bit more faint now, but it's you can still see that pattern. So maybe it's not that profound. Maybe someone has a simple explanation for it, but I think that's quite interesting, and it's something worth looking at it in future. Maybe actually going to these places and obtaining ground truth data or high-speed video footage of what's happening here. And then, of course, the further work, most of which will be my master's, would be to now correlate ground strike point density to elevation, as well as change in elevation, and see what I get. And then compare the flash density results and the GSP density results. And maybe consider peak currents in this research. Maybe there's something in that that could provide a good explanation. So I've written a conference paper on this work you've seen tonight. So if anyone wants to read it, feel free to contact me. My contact details are there on the screen. And thank you for your time, and thank you for listening to my presentation.
Right, thank you very much, Andrew. And apologies for dropping out there. I'm not quite sure what happened. My machine just decided it was time to switch off for a moment. But I'm glad to see everyone moved on smoothly. Our final speaker now is Salal Bordenov, and he's the head of marketing and sales at METEORAGE. And Salal will be talking to us about some of the more applications we have that come with METEORAGE's platform, but he's a well-experienced character working within the meteorological services and projects in Europe, and working based from France, of course. So Salal, please go ahead. Thank you very much.
Thank you, Hugh. Hello, everyone. So thanks to Stefan, Roydal, and Andrew, you had an overview of lightning detection techniques, of the standards, the SAIEE, and some of the research applications. I'm going to go briefly through more operationally what can be done with lightning data, and more specifically on lightning statistics, given that it was quite a focus of today's presentations. So related to lightning statistics, typically this is used beyond research. This is used operationally for various uses. The first one usually is to optimize the lightning protection system, so it can be used by the experts to serve as a basis for the lightning risk assessment studies. This can also be used for the operations, so to use the various components of the lightning risk statistics, not only one value, but to have a overall understanding of the risk, to optimize the procedures and adjust it based on the risk for the specific site and operations, and to also adjust it temporarily if there's some risk at specific periods. Obviously, to keep it efficient and to make sure you stay safe, the lightning statistics that need to be used must be standard compliant. So Stefan presented in detail the standards and the way also it recently evolved. So this is quite important to have reliable data and to have reliable products based on those data, so that you sure that the information you use for your operations is reliable and safe. The ones we provide in South Africa, thanks to the partnership between the South African Weather Service and METEORAGE, the statistical products that are provided are based on 11 years of lightning activity, as is a standard in South Africa, so that you have a full solar cycle. The first level of information usually is just the values. So having typically one lightning density value for a site, which can be used for the risk assessment, or other type of values being based either on the intensity, on the number of ground strike points or flashes. So all those values, it can be provided for a site, can be provided as a spread. So we can have different level of analysis based on those. We also produce and we also provide statistical maps. So kind of similar of what Andrew showed. So you can have an understanding of how the risk is evolving geographically over an area, how to compare the different regions of a site or the different regions of a network. And then we go to the most complex ones. The one we have, which is a bit standard, is a site statistical study. So for this one, we will dive in depth into all the risk components, all the lightning risk components for a given site. And then we also provide tailored studies. So for statistics, obviously, there's many different uses. There's many different ways to see the risk and to apprehend it. So for those, we always discuss with the users to understand really like what he needs as lightning information and to provide a matching product. So to dive a little bit better into the lightning statistical values, the typical one is just the lightning density. So just to provide the PDF with the NSG value. This is something that can be provided with the SAIEE data. And this is what is now recommended by the standard because it's reflecting better the reality of the risk by using the ground strike point and not just the flashes. We also provide those similar data for the lightning events themselves if you want to have a count, especially, for instance, to study lightning season or to study over a longer period of time for specific sites. If you had specific moments when you had more activity or when you had to compare between different sites. We also work on the number of thunderstorm days, understood as any day where you had at least one event detected by the network, and also on the electrical characteristics, so the intensity, the polarity. For those ones also, it's important to have reliable data and to have a network properly able to detect those ones. One of the interests, for instance, can be to compare it with lightning protection systems you might have on the site. If an impact is above or below the level of the protection systems, it might play on how it will be dealt with the insurance in case of incident, or if it's protected enough, or if you need to address the risk a bit differently. So comparing the spread of intensity and the mean intensity for your site is quite important. The polarity as well, given that positive strikes have specific characteristics, are more prone to continuous currents, are more prone to dangerous phenomena. So this is also a good indicator related to the risk and related to how you want to mitigate it. Those ones, if it's just one value, usually the best is just to have it as a PDF. So you have something which is going to be an official form that you can add if you're lightning experts, use that you can add in your studies. If you have some reports to make internally, that can be added to that, to have something which is stamped by the source, which is values that you can rely on, that you can prove the quality. And obviously, all this is measured in compliance with the standard, because this is quite critical when we deal with safety, especially. We want to make sure that all the values are based on the best practices. Regarding maps, the idea here is really to understand a bit, as Andrew explained, like for his study, you want to see how it's gonna evolve, how different it's gonna be over an area. If you have some specific areas which are more affected or less affected, and to understand all the phenomena behind that. So the most typical ones are gonna be grids, where we're just gonna produce values for each of the pixels. This also can be provided in different ways. Most notably, we can also do it along assets. So for an electricity grid, or for gas pipelines, or railroads, or highways, and so on. All this, we can integrate the user data. We can integrate the description of those assets and compute values along the lines, so that for each segment of the infrastructure, you know which parts are the most affected, what is the risk level differentiated segment by segment, and then that's a way to adjust the lightning protection, to adjust the procedures for each segment. So it's a way to both stay safe by making sure the most at-risk segments are properly protected, but also to save on those costs, which can be rather high for some type of infrastructures, by not overprotecting the parts which are the least at risk. Here as well, we consider lightning density, but we produce the same maps, and we study it in the same way for the number of thunderstorm days, for the intensity. We can provide it also for checking just the most severe events. So there's different ways to look at the risk, and it can be provided as image. We also provide those ones as KMZ format. So it's a way, especially if you already use Google Earth to have your infrastructure in it and to look at specific portion of the map. That's a way to overlap the lightning risk and consider both at the same time. And in Excel file, in case someone wants to have the actual values behind the map, that's a way to play with those values and to also do some comparison and do some statistical analysis of the risk. All those, again, compliant with the standards, obviously. Now, when we go in the most complex ones, if you have a specific site, what we usually provide to the users and what we usually use as a basis to discuss with them about the risk is what we call the site statistical study. So in this, we really provide all the components, all the ways to look at the risk. So the first one is just a summary, where you will have the lightning density values, you will have the maximum, the yearly maximum of the period, you will have some information about the amplitude, about the number of events above a certain threshold. So that's a way to have a quick snapshot of the risk of your site. And then we will go into each of the risk components. So the spatial analysis again, check if there's any hotspot around the site, if it looks quite homogeneous, or if maybe there's one direction which is more at risk than the other due to local climatology, to local topography. Then the electrical analysis, where we're going to look if you have maybe stronger, maybe not that many lightning flashes, but maybe of like more of the strongest ones. So that might be an issue depending on your protections. So check a little bit that side of the risk, as well as the polarity, the spread, the spread along the electrical characteristics, and the temporal analysis. So to know during the year if it's rather homogeneous compared to other sites, or if you have specific months which are more at risk. Usually, obviously, it's in summer, but you might have some months which are more at risk for your site than for other regions around, to check not only during the year, but also even within months and within each day. So to know if hourly you have more risk in the morning, in the evening, in the afternoon. So that can be a way to adjust your activities. For a given site, quite often you might have specific activities during the day that are the most dangerous, like moving around dangerous products, dangerous materials. So those ones, that can be a way to do this particularly at-risk activities at the time of the day, at the time of the year where you have the least, the lowest risk. This one we provide it as PDF, but again, all those studies, every time we discuss with the customer to make sure we understand the risk, especially if it's a complex configuration, if it's a network, or if it's like a series of sites, that can be a way to adjust it. And it can be one snapshot, but it's also quite interesting sometimes to do it repeatedly, especially if there's significant changes into the infrastructure, into the site. Say you had a first study before you built a new site, a new wind farm, a new power line, and then checking this period before the installation and checking the period just after, the year following it or the few years following it. That can be a way to see if the change in the site had some impact also on the risk. If you had some wind turbines, quite often it's gonna obviously create more risk for those turbines because they're so much higher than the ground previously. So checking the evolution of the risk is also of interest. So this one's were on the statistical side itself, but all those statistical values, we also use it for something a bit different for the products which are related to lightning alarms. So when you need to get real-time warnings related to approaching thunderstorms, we use it for one part of the international standards related to those products, which requires to prove the alarm effectiveness. This is quite an important point, and that's something that's not done by many thunderstorm warning systems. So we can't, as many other products, it's important not to just assert a number without any proof behind it, but to actually check for this site, for this configuration which is used, what is the effectiveness, how well it's gonna be able to alarm in time with enough ahead time whenever a storm is coming, and also make sure that you don't miss anything and that you have something which is efficient for your own operations, so that you don't spend 100% of the year under alarm, or that you have too many alarms and then you end up not using it anymore. So this is why for each customer we really optimize it based on the specific site. So we replay past time data. We try different configuration, so different radius for the monitoring area around the site where we're going to alert if something is coming into it. For the threshold, so if we want at the first flash you have inside the area, or if we wait a bit more to make sure to alert only when there's severe storm and not just scattered activity. and also the time to clear, so how much time we wait once the storm left the area to say that they can restart working, they can restart the normal activities. So all this we're able to thanks to past time data, we're able for specific sites to give the various parameters, to give the probability of detection, failure to one ratio, to give the number of alarms they can expect per year, and with the customer, based on the procedure, to decide what is the best balance between safety and something which is operational. So focused a bit on the statistics and the way it can be used for different products. Obviously, we use also the lightning data for other type of products. For alarms, we just talked about it. For observation interfaces, when you need to monitor the thunderstorms and lightning activity in real time. For lightning reports as well, both regarding distribution with insurance, with the optimization of inspection processes. So I'm not gonna go into too much detail now because like this we'll have some time for questions as well. But we'll be very happy to talk with any of you if you want to discuss more any needs you might have related to lightning data and lightning services. Thank you.
Thank you very much, Salal. So that brings us to the end of all our presentations, and I think we have some time now at the end for a few questions. So please go ahead and post questions in the chat there, and I will relay them to our presenters, and we'll get some answers. So I think there's a new one from Ferdinand here. I think that's directed probably to you and Stefan, Salal, but let me read it out, and you can, one of you can address it. We normally use SANS IEC 62305 for NG for our oil and gas projects. Can access to IEC 62858, not SANS 62858? Well, actually, maybe I'm best positioned to answer that question there. So currently the 62858 standard is not yet adopted by SANS, but it will be soon once the new IEC edition is published. And then it will become a SANS standard as well. I hope that answers your question there, Ferdinand. Anything, Salal or Stefan, you want to add there?
Well, no, I think you're right. You should be right, Hugh, because IEC is an international standard, but what I understood is that this international standard, which is you can see this as a reference, can be adapted according to the national committees, depending on the particularities of country, etc., etc. So the best, of course, is the international standard by itself, but of course you can follow the recommendations of your national committees, I guess.
Yes, and it won't, unlikely it will change much in any form. Right, there's and Rydal, I think this might be a question best answered by you, from Annalise, saying, how did they decide where the lightning detection sensors need to be placed? Will it be expanded further in future, or is it not necessary to do so?
Thank you, Hugh. Yeah, I'll take that up, no problem. Firstly, what we had is the network was originally a project between the South African Weather Service and our power utility Eskom in South Africa. And what we did is we engaged the market to find out what is the best sensors available in the market. And then we grid divided the country into sectors so as to see how best to optimize the locations of the network. And then we've started the deployment around 2005 with a review around 2010, 2011 of the network. There's something we call a MPEP in the network that we're currently using. That stands for the Network Performance Evaluation Program. And that gives us an indication of the best performance of the network at current, which then gives us the opportunity to reposition sensors according to that grid that we've worked out and how best to optimize it for the best performance that we can get, as well as depending on the topography of the country in the respective areas. So you would have noticed that there were some changes made. We started with a network of originally around 19 sensors, and at this point moved up to 26 sensors. And that was based on that evaluations that we then had to reevaluate the performance of the network. And we're currently sitting at a network where we've got between sensors a rough estimate of about 220 kilometer radius. I hope that answers. Thank you.
Thank you, Radel. There's a couple of questions going back a bit, so I'll just address those, and then I'll address the more recent question. There's a question from Walter asking, are there softwares that one would recommend for simulating the calculations, or are they just IEC based? Many softwares don't have the South African earthing system TN-C-S within them, and that is a challenge I've encountered. I don't know, Stefan, that was asked during your presentation. I don't know if
Yeah.
relevant to that.
Yeah, I'm not sure I'm the good guy to answer such a question, because I think in the question what I understand is that it is referred to programs to compute and to address the risk assessment itself. I mean, describing the assets, the buildings, and the earthing system, etc. And so you put inside the landing density, and based on the topology of the building, and then you get a result on the level of the risk. So I'm not the good person to answer this, I'm afraid. And I think somebody like Alain Rousseau or other experts in the domain could answer this question. But I'm not sure that all these programs follow, strictly speaking, the EAC standards. So I would say, yeah, pay attention and ask questions, maybe. Yeah.
Yes.
Sorry, not to answer your question.
No, not at all. I think Walter also, just on that note, as far as I'm aware, the IEC software that was developed at one point is actually, for some reason, I can't remember, there were some issues there, and it actually isn't that available anywhere itself. So from a risk assessment point of view. But if you are referring to software that's more about some design considerations, that's a different area altogether. I'm going to take the next two questions together because they actually will, and Stefan, but maybe this is a good one. I've got some things to add on here myself, but I'd like to hear what you think. So firstly, there's a question from Mike Fisser saying, lightning data is typically linked to the 11-year solar cycle. Any reason why was that changed 10 years? And then just to combine that maybe with a question here from Ferdinand again, which is, any observed changes in NG or NSG due to global warming? Probably recent data. Stefan, I think those two questions dovetail a fair bit. Do you have any thoughts to add there?
Yeah, challenging questions. The first one mainly. Solar cycle. This is true that there are some papers, and not only the paper that was given going along with the question, but more recent paper. It's not evident that there is a link with the solar cycle. So in some cases, there are some trends in some regions in the world, but at the same time, in other regions, the correlation is very low and very weak. So really, scientifically speaking, there is no evidence on that. And but nevertheless, the choice of having 10 years is really driven by the fact that we want to make sure that if the main idea behind this is that if the data set duration period is too long, we might include in this data set some change due to some trend, due to the global warming. And this comes to the next question. So there is no evidence of global warming effect on the lightning counts, let's say. I would say that even in France and some friends in Europe have made a similar study as us. The trend is even that despite the fact that the LLS is becoming more and more sensitive and more efficient, so it seems that the trend in the counts of number of lightning flashes is decreasing a bit yearly. You mean? Of course, it's varying from a year to another, but the general trend is even decreasing, and this is not in line at all with what the expectations and the forecast of the experts in climate says. That they are just saying that we are going to have more and more thunderstorms because of the heat elevation and etc. etc. So again, there is no evidence. I think we are having a lack of observation because the climate, usually you are running studies with at least 50, 60, 70 years of data. Regarding the data from LLS, it's very recent systems, and if you want to make sure that you deal with very high quality data, it's 10, 15, 20 years maximum. So, and it's very hard to identify the trend in this. So again, so these questions are really hard to answer. And so far, in my opinion, there is no evidence. But maybe you are much more.
No, I would agree.
Aware about that.
I would agree with you on both things as far as I can see. I know Professor Earl Williams really wants to tackle this, but in order to do so, he's trying to get records of Thunder Day or Thunder Day data going back over 100 years in order to properly answer the question of, do you see a trend? As you say, the 30 to 20 years modern lightning location systems have been active is not really enough to actually answer the question of, or do you see a change due to global warming? Your timescale needs to be much longer than that for that type of study there. Thank you, Stefan. Much appreciated. I think that brings us to the end. Unless, are there any final questions that anyone wants to pop in? But if not, thank you all to all you presenters. Thank you very much for your time. And thank you for a very interesting webinar. And thanks to the audience all for participating. And I think with that, we can finish. And the recording of this will be available on the SAIEE's YouTube channel. Fantastic. Thank you, everyone.
Thank you very much.
Yeah, thank you to all.
Have a good evening.